Okay, we can also find the acute angles between lines and planes. Now, on the PowerPoint, they show the diagrams in 3D, so they show you the planes and everything, so it's worth having a good look at that. I'm not going to draw in 3D though, so I'm going to show you how you would probably do it in an exam, which makes it a bit easier for you to sort of imagine as well, maybe. So, we've been asked in the second example. Okay, so we've got find the acute angle between the line L, which has got the equation, can't quite fit it in, R equals 2I plus J minus 5K plus lambda 3I plus 4J minus 12K, and the plane with equation R dot 2I minus 2J minus K equals 2. Okay, so like I said, they do it in 3D on the PowerPoint, but if we think of that in 2D, if this is my plane, I'm going to do it as a dotted line. Okay, I'll tell you what, I'll do the plane as a solid line. If this is my plane, and my line L is coming here somewhere, okay, this is my line L, then bearing in mind the equation of the plane, this is the normal vector, so the normal would be here, because it's perpendicular to the plane. Okay, so this would be the normal vector. Okay, so if we taken it from there, the normal to the plane, n equals, remember it's this vector here, okay, so it's 2I minus 2J minus K. Okay, and then we've got, so we know the normal here, we also know the direction vector of the line. Okay, the direction vector of the line, so the normal to the plane, I'll add in there, is in direction, and we've also got the direction vector of L, which is this part here of the line vector equation, so it's going to be 3I plus 4J minus 12. Okay? Okay, so when we're working out the angle between them, then we know these two. This is actually the angle we're looking for. Now on the PowerPoint they do it slightly differently to how I would. I would stick personally to finding the angle between these, because these are the vectors that we've got. Okay, so let's call this theta. Okay, so using what we've already done, these are now basically, we can think of these as almost two lines, so we can do the fact that cos theta is going to be equal to n dot this vector direction of L over the modulus of this times the modulus of this. Okay, and that's going to give us this angle here. Alright, so cos theta is going to be equal to 2I minus 2J minus K dot 3I plus 4J minus 12K all over, I'm going to give myself plenty of space here, all over the square root of 2 squared plus minus 2 squared plus minus 1 squared times by the square root of 3 squared plus 4 squared plus minus 12 squared. Okay, so remember this is cos theta. I mean, I probably could have jumped straight to this line where I do 2 times 3, add minus 2 times 4, add minus 1 times minus 12. You could have skipped that step and done this step straight away for the dot product. And that would be all over the square root of 169 times the square root of, that's a 9, sorry, square root of 9. So cos theta is 10 over 39. Okay, so that's going to give us theta is 75.1 degrees to 1 decimal place. Now remember, that isn't the angle between the line and the plane. This is the angle we actually want. Okay, let's call it alpha if you want. This is this angle that we've just worked out because we've used the normal vector direction and we've used the direction of the line L. So we've worked out this angle, but now we can literally use angles in a triangle to work out the angle that we want. Okay, so we can literally do alpha would be 180, take away the 90, the right angle in the corner there, take away the 75.1 degrees that we've just worked out, and that's going to give us 14.9 degrees as our angle between the line and the plane.